Okay, so we still only have 30 students. I think we should double that number. I think we will wait for maybe 3 minutes. Okay, and then we'll begin.
How are you doing today, Dr. Yan?
Yeah, good. How are you?
I'm doing all right. It's just a Tuesday.
Yeah. Yeah, I think students are coming, but we still should wait for maybe 20 students. Right, so taking this time, do you have any questions so far regarding this course? Yeah, feel free to ask now because we probably still need to wait for 1 or 2 minutes. Okay.
Not really a question, but man, my sample for the assignment had a lot of colonies.
I see. That's a little bit liberal, right? So yeah, so you have 2 samples, right? So to work on, right?
Yeah. Oh yeah.
Got it.
I just thought it was funny. One of them had maybe 70, and the other one had close to 300. It was gnarly.
Oh, really? Oh.
Yeah.
So we didn't check the balance. So maybe some only have a few, but some has crazy number. Yeah. Yeah. Thanks for the efforts because this will be later shared by all students, and then, you know, the for final project, then you will be able to use that to work on.
Very cool.
Yeah, I think we should begin, even though I think the attendance is not so good. All right, so just a recap, because that's a midweek, right? I'm not sure how many of you still remember what we discussed. Right, so basically what we talked about SVD is that we start from the SVD shape, right? We ask you guys to remember this shape. You have n rows, which is like n data items, and d columns, which are like the attributes, okay? And we wanted to do some kind of dimensionality reduction, right? So if you look at here, right, this is kind of like, let me see, okay. Yeah, it's different mode. Yeah. So basically, you go from d-dimensional space to r-dimensional space, okay? And how many dimensions, right? So the first dimension is the most important. This is called the first singular value, okay? The second singular value. So this is a diagonal matrix. That's why we have D, right? And for each dimension, the true dimension vector is recorded here, okay? So because this is V1 transpose, because V1 is a column vector, V2 transpose. Okay. So basically, it's kind of like it cannot be mentioned as a dimensional reduction because we have not reduced this dimension yet. Right? So it's just that this matrix contains only R dimensions information. Right, a lot of redundancy here. Okay, and maybe not really D-dimensional space, only R-dimensional space. Okay. And but you can further reduce maybe some of those lower singular values, right? Those dimensions are really noise. You can remove them. This gives you the top K dimensions, where we see that this is the AK, right? So this is A, but you can have an AK, right? So if you look at AK, it's basically a simplified, the first K rows and the diagonal matrix, the first K diagonals, and then the first, K columns. Okay, right. So this is the result is AK. Right. And we asked you to memorize some of the conclusions, right, when you use them. Right. So you know that these are the dimensions, and you are, but they are all orthonormal, which means each of them are unit vectors. Okay, this is also a unit vector, and any two of them are orthogonal. If you look at the vector space, well, this is 1, this is 2, okay? They are orthogonal. Okay? They are 90 degrees, basically. So, and yeah, just a quick recap. Okay, so, and the shape, right? The shape of this shape is actually equivalent to this formula. Okay, because if you look at UI times VI transpose, it's actually a matrix, right? So this UI is a column vector, and VI is a row vector. Okay, a column vector times a row vector is a matrix. Okay, so you have basically each dimension, right? Each dimension I define a matrix, and you have R matrices summed together. Okay, if you only have K of them summed together, then it's removing some noise kind of data. Right? It's like a reduced dimension K. Okay, and we also reviewed so there's a relation between eigen decomposition and the SVD. Right? So basically, SVD in the eigen decomposition, the difference is very, very small. Okay, so actually you can use SVD to do eigen decomposition. So basically, if you work on SVD is any matrix. Okay, if you for this A matrix, right? If you compute A transpose times A, right? Then you can do eigen decomposition on this. Right? It's the same thing because you see this A transpose A times VI is equal to a lambda times VI. Okay, so basically, if you compute the A's covariance matrix, this becomes positive semi-definite. Then you can use this as this becomes a symmetric square matrix, right? And then you can do eigen decomposition. They are basically equivalent. Okay, we will see more details later today. So these are the conclusions we push to you, right? So why they are correct? So then we have a few slides proving those theorems. Okay. Firstly, we are looking at V's. We say that V is so-called best fitting lines, right? So we define this sum of square projections criteria. Okay. And we say that we really want to maximize the sum of square projections. Right? If most of the information are projected on your dimension, then this is the best dimension. Okay. And when we find the second one, we want to be orthogonal to the previous one. Okay, so this is general case. Right? But once defined V, we show that V is the best fitting space. Right? So it captures most of the information of your data rows in A. Okay, and this we proved, right? So by induction. And then so far we only have V, right? So what about singular values, sigma and also U, right? So here we first define them, and then we put them back, and we show that they put back in the previous three matrices format. It's really A. Okay, so we are just using a constructive way to prove this. So here we say that remember that criteria is actually L2 norm square, right? So if we without square, basically it's like A VI is a vector, right? You take a square root of x1 square plus x2 squared, L2 norm. Okay, and then that thing is really your singular value, okay, the I singular value. And so you can see once your V is defined, A is a constant, right? And you can always compute this one. So which means your singular value is defined. And with a single value and v are both defined, and a is constant, you can use this to define u. Okay, this is constructive because we basically we tell you that there's a conclusion. Right? So a vi is equal to sigma I ui. Okay, so we are constructive. So this becomes sigma I. But the magical thing is that if we define those things like this, then we put them back, we really get a. Okay, put them back into the matrices. Okay? So let's continue to the next page. Right. So this is where we prove the correctness. Right? If we put back into like this shape, and we explain this shape is equivalent to the matrix multiplication. Right? And if we put them back, and it's really correct. Okay, so we spend some slides to show this. Right? And then we show that there's a relationship between SVD and Frobenius norm. Right? Basically, the summation of the diagonal, right, the singular value square, okay, is equal to the Frobenius norm. And Frobenius norm is really every element in the matrix A square and takes the sum. Okay, and it takes square root, but because we have this 2 here, right? So we don't need to take square root. Okay, so these two are basically the same, which means all your information of all the elements squared and then take sum is totally captured by the singular values, right? You just square the singular values and it takes the sum. It's the same value. So this is what we see last time, right? A conclusion. And now then we go to AK, right? As we said, right? So remember our singular values is go from big to small, right? Because this is how the projection goes, right? For V1, the largest projection is sigma 1, okay, right? And then what if this later, the rest of those sigma i's are very, very small, right? And then that's likely they are noise. Right? For example, if you think people are measuring the vectors in this screen, okay? But somehow there's a small component outside the screen because the measurement error, right? But this component outside the screen is actually a noise, right? The associated component, the sigma I, will be very small. Okay? Maybe removing it will even improve the data quality. Okay, so that's also why if you do a PCA, dimensionality reduction on your data, sometimes your machine learning model can be more accurate than before, right? Because there's an effect of removing noise. Okay, and so now we only consider up to k. Okay, we don't consider originally it's r, right? So we go from r to k, right? So this gives you AK. And we show that if you measure in Frobenius norm, okay, and you consider, you only allow approximation of A, that is, have less information, right? Only allow k-dimensional space, right? Less than or equal to k. Then AK is actually the best, okay, compared with all other possible matrices of rank k, or less. Okay, so this is what we proved last time. I hope you still remember that. And when we stop, is actually we want to show this conclusion for another distance, right? So this is one distance, okay? Right? Because if they are the same, then every element is 0, therefore Frobenius norm will be 0. Okay? In machine learning, if you know, you took my machine learning course, you know that Frobenius norm is a kind of preferred, right? Because if you take the derivative of Frobenius norm, you'll get something like a trace kind of like operation where you can easily take a derivative. Okay? And you can do gradient descent, basically. But then we stop and at where we want to show that this conclusion also holds for 2 norm, right? So basically replace this f with 2, okay? And it's also holds. And today we will prove this and begin with proving this, okay? But because it has been 1 week, so we will recap. Okay? But we will not go into the proof. You can rewatch the video. Right? And in order to explain what is 2 norm, right? Because we have the matrices, we have the 2 norm. We actually define it here, right? So basically, if you have a unit vector, right, you do a linear transformation over A for all possible unit vectors, right? You want to find this one that after transformation is the longest, right? So that's the norm. Okay. Of course, we need to normalize, right? So here, all you restrict to 1, or you divide by the length. Okay. Of course, you do not allow this to be 0 because divided by 0 is not defined. This is because superior. So this is the upper bound. Okay, so the reason we have this is because sometimes you have a number that is very close to that. You can get infinitely close, but you cannot reach there. Right? So, for example, one example is 1 by x. Right? So there's also an INF in 0. Right? So no, so you can get infinitely close to 0, right, if you increase x, but you can never reach 0. Okay, so then we say the lower bound is 0. Okay, so this is like a max, this is like a mean, but sometimes it cannot be reached, but you can get infinitely close. This is a mathematical, this is a calculus kind of thing, right? So, and so 2 norm is actually, just defines things like, make p equal to 2, right? So this is all we say, hey, this is 2. But if you remember, this is exactly, sigma, right? So sigma I, okay? Whereas if this is vi. So here, so we will consider the v1, the most informative dimension. Right? So this is, because this reason, the 2 norm of A is exactly the first singular value of A. Okay? And we also have this relationship, which you might want to remember. And then we go through an example where for document, right, term, right, document term, we can do a dimension reduction instead of the original dimension. And we show that the cost can be significantly reduced. Okay? Previously, if you directly work on the original matrix, it will be n by d. Right? So let's say you have 10,000 documents, each has 10,000 words. Right? So this will be huge. Okay? The 10,000 times 10,000. Right? Now, if you have a reduced dimension k can be a small value, 10, maybe d, and then it becomes 10,000 times 10 plus 10,000 times 10, right? Instead of 10,000 times 10,000. So this can significantly reduce the computing time. That's why we will prefer a dimensional reduction here. Okay, you still capture the top k most important dimensions here. And the one interesting thing here is that we can upper bound it, right? So think about it, right? So here we say that this is the max of the unit vector rotating on all directions, right? And then do the linear transformation, and the largest possible value vector after this linear transformation, right, is actually the 2 norm. Okay, so we have this 2 norm, and then we want to show that, hey, this 2 norm is really sigma k plus 1 because it removes the first k dimensions. Okay, but so far we only have this conclusion, right? So this conclusion, we only know 2 norm is sigma 1 of this what's inside. Okay? So basically, we want to prove that this thing is sigma 1 what's inside. Okay? We want to prove this thing is equal to sigma k plus 1. So basically, we say that if you're A and you take out the first k dimensions of all the information, right, and the rest of them, if you look at the singular value, right, the first singular value will be sigma k plus 1. Okay? That's the next dimension. But in order to prove that, we first need to show that UIs are orthogonal, right? The reason is very simple, because we construct UI. Right? So if you remember how we define UI, it's a constructive, right? So we have UI is equal to A VI divided by sigma. Okay, so this is how we construct. But there's no guarantee that U1 complete like this and U2 complete like this, they are orthogonal, right? Unless you prove it. But if this is really the case, and here we actually spend the last last part by proving this theorem. Okay? We show that this is really the case, and we prove a special case, which can be generalized to the other case. Okay? We construct another vector, V prime, and then we show that if you have some component, right, they are not totally orthogonal, equal to 0, then there will be contradiction. Okay? Well, we use the generalized Bernoullian quality. We'll use this again today. So it's better to remember those very commonly used inequalities, which helps you a lot in the derivation. Okay? And we show that this is impossible because, sigma 1 is the largest possible value after you do the transformation by A over a unit vector. Right? And then we show, hey, this is a unit vector, and transform by A, you get something larger than sigma 1, even after mapping to some dimension, which means a component of this vector. Right? So that's a contradiction. And here is a recap of what is a singular vector. A recap of what is a Bernoulli inequality. Bernoulli inequality is saying that, you have this number, it's to the power n. If you can put the n down here, okay, you put the n from to the power of down times this x. Okay, if you do that, typically this is larger than. Okay, the only exception is if your a is n, and if it's an integer, then it's always like that. 2, 3, 4. Okay. 1 is equal, so because this is 1, then 1 plus x. Right hand side is 1 plus x. Well, if your a is within 0 and 1, right? So then in this special case, the sum will be reversed. Okay. Otherwise, it's always larger. Right? So this is also very easy to see, to memorize. You just think about what is 1 plus x to the power 2. Right? It is equal to 1 plus 2x plus x squared. Okay. Yeah. So you, of course, you have another term by 2x. Okay. Oh no, 1 plus 2x this term, right? You have x squared. X squared is always positive. Okay, so that's why this thing is larger than 1 plus 2x. Okay, yeah, so just use this notation. You if you cannot memorize which direction it goes, just put the 2 here. Okay, but generalize to any number that is larger than 1, including the real values, not just integers. Also less than 0. Only when it's between 0 and 1, then you are smaller. Okay. Two special cases, if it's equal to 1, then this is 1 plus x, this is 1 plus x. That's equal. If it's equal to 0, right? A equal to 0. So this to the power of 0 is 1. Okay. This to the power of 0 is also 1. This times 0 is 1. So they are also equal. Okay. So only at these two special values, they are equal. And again, just keep in mind, okay, because we will use it again today. Okay. When you put this number here down, right? If this is a negative number or if this number larger than 1, then you can times this to the power with this number x here, okay? And you are safely knowing that this will be small, go smaller. Again, we will not prove this, right? So, but this is a very famous inequality. So there are probably 10 or 20 inequalities that serial people are heavily using them, right? Like math people, okay, to derive different kind of things. Any questions so far? I think this is where we left over here, right? So, and I think we also proved this, right? So now that we know that the different dimensions of U are orthogonal, we prove this here, okay? So here we are using the conclusion that UIs are orthogonal, right? Because if U are orthogonal, let's say these are orthogonal, right? This factor orthogonal, this is the value. Okay? This is another value, right? Because the inner product of VR, right? It's actually 1. Okay, so this gives you this. Right? So go from here to here, right? Why it's a coordinate square, right? So it's like U1, U2 coordinate square, right? This only happens if they are orthogonal. Okay? So we are using orthogonal, then we prove this. But it's nice that this is bit by bit, so to get you convinced that everything SVD can be proved. Right? So we stopped right here that we want to show that for AK, which is the top K dimensions that we take, and for any matrix B, at most K dimensions, so many information. Right? AK is the best, closest to A. Previously, we showed this for Frobenius model. Okay, we want to show that this also holds for 2 models. Okay, so this is where we leave behind, and we will continue today. And before we move on, because previously it's a recap of what we covered, right? The conclusions. We will not go through the proof again, but you have the video, you can watch the proofs, okay? That's quite intensive actually. So from now on, we will go again back to the proof, okay, of the theorem. Okay. Before I move on, any questions? Okay, yeah, please go ahead.
Like, can we do any examples like after the theoretical part or no?
You mean examples of what? Hello?
Yes. Like examples of the things we're doing.
Oh, what we are doing. What we are doing actually, we are proving like a SVD, which means, A can always be factorized into.
No, I don't mean like this topic in general. I mean in general.
in general, you want to take an example of SVD? Is this what you want to say?
And that's what I'm saying. Like, I don't mean any topic specifically, like in general.
Yeah, I don't quite understand, but we can discuss offline. Okay, so you can send me email.
Okay.
Yeah. So yeah, so here it's a more theory kind of thing, right? We prove that SVD can really be decomposed like this, and we have another slide telling you the applications of it. Right? So when you are familiar with those properties, right? So it's like magic, right? You know that any A can be decomposed into this kind of thing, right? And then you can do a lot of derivations later, okay? And you will be convinced, hey, these nice properties are there, and you can really use them to do something. We will see two applications using SVD, okay? But SVD is in general very useful because when you do any derivation, you can first you know that A can be decomposed like this, right? Then a lot of further derivations can continue with it. Any matrix can be decomposed into I from 1 to R, which is the rank of the matrix, and then do something. Especially because these things are orthonormal. Right? So, and you can see here our derivation will also show you that orthonormal is super useful. You can cancel a lot of things in the proof. So here, let's look at how to prove that AK is the closest to A, even when we measure in 2 null. This is 2 null. Okay. Right. So firstly, if your rank A is less than K, which means your R itself, right? Your R itself. So your A can be equal to summation of to R, but R is less than K. Then we are done, right? Because here we are just taking all the dimensions, right? Okay, 1 to R, because R is less than K. Okay, so this matrix is exactly this matrix. Okay? We can take all the dimensions. So this is equal to 0. So we are done. And so what our focus will be that A is really more complicated than AK. Right? Need a little bit more dimensions than AK, but maybe some dimension noise. Okay. So now we are focusing on this case. One thing that we should already know is this. Right? So if you remember, you see that if you consider this 2 norm, it's equal to what? It's equal to sigma 1 square of A minus AK. Right? Right? And equal to, basically we take out the first K dimensions, right? It's from K plus 1 to R. Okay? If we do something like this, then this first singular vector is K plus 1, VK plus 1. Okay? And its corresponding magnitude is this. So this is what we already proved. Right? So let me see where we proved. So this is F. Right? So we are now proving F also holds for T. Okay? So let me see where is it. Yeah. So we already show here. Right? We already show something here. Okay. So this is just using this conclusion. Right? Right. So this is using the previous conclusion. Okay. So now what we want to show is that for any matrix B with rank less than or equal to K, right? This thing should be no smaller than this thing. Okay. Which means we can just put it because it's equal. Right? We can put it this here. We want to show that this thing is no smaller than sigma K plus 1 squared. Okay. So now, in order to prove this conclusion here, right? In order to let me see. I think I should click. So in order to prove this thing, we just need to prove this thing because this thing and this thing are equal. Okay, this is what we just basically concluded. Okay. Now let's consider how to prove this. Right. Yeah. So firstly, in order to show this, we need to consider. Remember, we totally have rank up to R, but B is only rank K, right? So we definitely, and the A is actually a matrix of n by D, okay? So if you think about this, can be d-dimensional, right? N is usually much larger than D. So if you look at the rank, it's decided by the smaller dimension. Okay, and B can be up to d-dimensional, right? But only k of them are allowed. Okay, so it can contain no information more complex than k dimension. Right? So the null space has at least d minus k, right? Because this is using our another conclusion. I think it's really early on. Let me find. Probably the null space, right? Probably here. So we are using this conclusion. Let me, okay, this conclusion. So your null space, that's a B's null space plus B's rank. Okay, B's rank is K, right? And plus your null space, let's say something question mark is equal to N. Okay. But we know that B's rank is less than or equal to K, right? So sigma is larger than or equal to N. Okay. So this is the conclusion that we are using. This is what we reviewed before. Now, so I think it should be previous. Okay. Now we know that the null space of B has at least the d minus k dimension, right? Because B's rank is less than equal to k. Okay, minus less than k. So you are larger than d minus k. Okay. So you think about the whole space of A is d-dimensional, right? This guy has at least the d minus k dimension. And if you look at the span of the first k dimensions in A, v1, v2, all the way to k plus 1. Okay? So how many dimensions do we have in this span? Who can tell me? How many dimensions in this span? Okay, so this is the answer is k plus 1. Right? There are k plus 1 of them. Right. So less than equal to k plus 1 if you have a span of k plus 1 like this. Right. But we know that we want it to be k plus 1 or something. Okay, so there will be no overlap of any information. So it's really each dimension the new dimension. Okay. So we have k plus 1 dimensions here. Right. And how many dimensions are there? So we know that it's at least right, larger than equal to 2 minus. Okay. Right. So they must intersect, okay, because totally we have d dimensions, right? If you think about it, if these d minus k dimensions are totally different from the k minus 1 dimension, so if we sum them up, we will have d plus 1 dimension, right? K cancels. But altogether, A has, we all together we have d dimensions. So this is a contradiction, right? So that shows that within these two spaces, okay, there must be some vector that's in their intersection. The intersection is not going to be empty. Okay, so that's what this line is saying. Now we know that such a z exists, right? So we can find such a z, right? And we just we can normalize it, right? So we can scale it to the length 1. Okay. Now we can always find a z like that, right? So what we can do is this is 2 norm square, right? 2 norm square is something we just discussed, right? So if you put some vector here, unit vector here, and rotate, the maximum possible value is this. Okay. Right now, z is yet one particular vector, right? That normalized to unit vector. Okay. So of course, this is larger than equal to this. Right. So I hope this is okay for you guys. Again, the proof is making sense to you is fine. Okay, it's very difficult to think about it. Right? So most like very smart mathematical people doing this. And so one thing you need to memorize is what is the null space. Okay, null space of B means if you B times matrix X equal to 0. Okay, right. This is null space. Right. So which means Bz is equal to 0 because Z is in the null space of B. Okay. It's in the intersection of two spaces, which means it must be in this space also. Right. So in this way, if you write the right-hand side out, it's AZ minus BZ. So BZ is 0. Right? We tell you BZ is 0. So that's why we only have AZ. Okay. But this Z is some vector in the null space B, but also in the first k plus 1 dimension. And such a Z must exist. Okay. We'll use this conclusion to derive the final conclusion. Okay. But so far, we know what is a Z. Right? Z is something in the intersection zone that we constructed. Okay. And we know that this conclusion always holds. Right? But our goal is not to prove this. Right? So our goal is to prove that, our goal is to prove this. Right? And this thing is, sigma k plus 1. No square. Okay, so here we have. So in order to prove this, because we have square, right, so we have, and we want to, this thing to be larger than or equal to sigma k plus 1. Right? Because we are proving this, but so far we only prove this. Right? So if we can show that this thing is larger than sigma k plus 1 square, then this thing is proved. Okay. So the next thing is we want to show basically this part. Right? We want to show this part. Okay. Any questions? I hope this is fine. Okay. Now we want to show this equation. Right. So this is the last slide. Basically, we are showing this, and then everything holds. Okay. So let's write AZ. Right. So write it out. So we know that A. What is A? Right. So A is something like this. Okay. So AK is to the power sum to k. A is all the way to sum to I. Okay. This is A. Right. And you times it to 0. And if you times, Z, what will give you? So what's the result? So how to see from here to here? So the answer is also very simple, right? So you look at what is this? This is a scalar, right? So this is scalar because this is inner product. Okay, inner product is one particular value. Right? So these two are both values. Okay, so then it becomes some value Ci times Ui. Ui are the different orthogonal dimensions, right? So Ci is like that coordinate, right? And because they're orthogonal, right? So if you compute, this is AZ is a vector, right? So this is a vector, and if you compute the vector length, right? So it's really that coordinate square, right? So this is one coordinate squared. This is another value, right? This thing squared. Okay? So this is how we go from here to here, because this result is vector. And the vector has different dimensions, U1, U2, U3. Okay? So if you compute the vector length squared, it's something like this, every coordinate squared. Okay? Any questions so far? Okay, so then let's continue. So here actually we have the R here, but we can reduce it to k plus 1. Okay? So why? Because this is that. This is that. If we go back to the previous slide, okay, this Z it belongs to the first. It's in the intersection of two space. It's in the intersection of two space. Null B and span one B1 to B2. So it's within the first k plus 1 dimensions. Okay, there's no component beyond the k plus 1 dimensions. Right. So from k plus 2, k plus 3, these components will be definitely 0. So these are equal actually. Right? In general, it will be larger than equal to. Okay. Right. But here it's equal because this Z is only belonging to the first k plus 1 dimension. Okay? Basically, it's this thing here. And finally, we can write out. You think about this sigma I, right? So, sigma I decreases as I goes up. Right? So, what we can do is we can take this. So if we put every sigma I into sigma k plus 1, okay, right? Which means, in this summation, the first term should be sigma 1 squared times this, right? But we reduce it to sigma k plus 1 squared. Okay? The second term should be sigma 2 squared, but we also reduce it to the much smaller value sigma k. Right? If you reduce all the previous values to sigma k plus 1, the k plus 1 term, of course, is still k plus 1. Right? Then this becomes a constant you can take out. Right? But of course, it will make things smaller. So that's why you can take this sigma, this is lower bound of sigma I, because from 1 to the smallest cube. Okay, and you can take it out, and then you have this term, right? So this term is 1. Okay, so this term is 1. You may ask why, right? So this is because, so if you look at z, right? So z is a unit vector. This is what we're doing, right? So the unit vector along the first k plus 1 dimensions. Okay, u1, u2. So they are coordinates. This is coordinate square is the vector length of z. Okay, so the vector length of z is 1. This is because when we previously, if you look at the previous page, we say that we have an assumption we already scale, we normalize that to this length. Okay, so that's why in this derivation here, we have this, because this is z along each dimension. It's coordinate, right? Okay, and then the coordinate square is 1 because that length is 1. Okay, so finally we got this. So, yeah, so what does this mean? This basically means that this thing, right, equal, larger than equal to this, right? So this is true. Okay, right? And now that this is proved, right? And we also know previous slide, this is the case, right? So of course, if A is larger than B, B is larger than C, it must be. Right? So we prove this is. Okay, and finally, you know, this thing is actually this. Right? So we prove this thing, right? So that basically completes the proof. It's a little bit complicated, though, right? So, yeah, any questions here? The key is actually to construct this intersection space. And we construct such a Z, and this Z is in null space, so we can make this 0 and we can cancel this term. Okay, and we'll go to here, and in the next page we will show that you only have components. This Z only have component in first k plus 1 dimension. Meanwhile, it has length 1, which is used in the next slide. We prove that. So, but such a Z always exists. Right? It's non-zero. Okay, you can always normalize it. That's why we can prove it. Okay. For example, here we are using the Z length is 1. It's a unit vector, right? And to get this equality. And from here to here, we are showing the fact that there is within the first k plus 1 dimension. Okay? So beyond the k plus 1, so there's no component. This thing is 0. Okay. Right. Any questions? I hope it is fine. Right. So because it's reasons, and you know, we know that even in 2 null, okay, AK is also closest to it. And for Venus null, it's also close to it. Right. So AK is pretty the best. Okay. Any questions here? Again, this is a little bit difficult, right? So as long as you can follow, that should be fine. So you don't have to prove this. Okay. As long as every step you understand how this is derived. And so next, let's prove. Sorry for that. Okay. Yeah, if you have a question, feel free to ask. Otherwise, please mute yourself. And so next, let's do a SVD analogy to the eigen decomposition. Okay. So here we can see that you know, this is we know this, right? Because this is how we construct UI. Right? We construct UI as AVI. Right? Okay. But this thing we have not proved it. Right? If you reverse, you transpose A, then if you time UI here, it's equal to sigma IVI. Right? So this is actually very close to the eigen decomposition. We have A x equal to sorry for the handwriting. It's equal to lambda x. Okay. But here the x will be different. Right? It's not just a singular vector. It's left. It's not the eigenvector. It's a left singular vector and the right singular vector. That's a little bit different. Right, so the first equation follows from the definition how we define UI, and we only need to prove the second dimension equation. Okay, so the left-hand side A transpose times UI is equal to, here we are using the conclusion. For now, you should memorize it. So what is A? What is A? A is summation J sigma J Uj. Uj, Vj transpose. Okay, so this thing you should memorize. Okay? Just look at, you have seen this thing many times. Okay? Now that you know this, right? So now we have A transpose, right? Which means it's this thing transpose. Okay, if you transpose, summation can go up, right? So which means the summation can just go up. Right? So we still have J. And this constant can go up. Okay? So which means we can do this constant. Okay? I think I didn't use the eraser. Okay? And finally, it's this term. Right? So this term is Vj transpose. Right? So if you do a transpose of something, it should be Vj transpose, right? From this direction. Okay? And Uj. So transpose stuff. Okay? So that's why we have Vj transpose. So that's what we get here. So just following the definition, A, we put it here and do the transpose. And we're timing UI, okay? And we know this diagram is, you see why, SVD is so useful. So when you decompose, first you know that it can always be decomposed into some strip like this, right? And then, they are also normal. Right? So if you think about this thing, this is inner product, okay? And I equal to J, then it's 1, because it's univector. It's a vector length square. Okay, but I doesn't equal to J, it's 0 because they are orthogonal, UI and J. Okay? So which means now here we take all possible J's, but if your J is not equal to I, it's going to be 0. Only one term remains, which is sigma I, VI, UI transpose. Okay, UI transpose UI will be gone. It's 1. So it's a sigma I, VI. This is how it's doing. So this basically proves this theorem, right? So the left-hand side is A transpose UI, right-hand side is sigma I. Right? But again, so you don't have to go through this reason. Right? So just remember, right? If you have the VIs are really our dimensions, right? Right singular vectors. Okay. If you do the linear transformation over VI, you will get a vector that is in the direction UI. Okay. And the scaling is exactly the singular value. And on the other hand, if you want to reverse them, right, so you want to time something like UI and get VI, right, so you need to work on A transpose. Okay. Any questions so far? Okay, I hope this is fine. So far, what we do is, if you remember, we proved a lot of things. Right? So show that, hey, you must be able to, so you will be able to define those V, right? And then you, based on V defined, you can define sigma, and based on sigma, you can define V. Yeah, that's true, right? So for example, if you think about here, right, for example, you have a unit vector. You can go all directions in the space, okay? D-dimensional space, a unit vector. And you just time A. You find the vector that makes the result vector the longest, right? And such a V must exist because you can try every infinite possible values and then find the largest. Okay, this max really exists. But we never told you how to compute this V, right? So if you cannot compute this V1, you only know this V1 exists. Right? That's okay, but that's not so useful, right? Because if you want to do SVD, you need to get those vectors, right? So if you look at, you need to get the VI, UI, and the singular values. Okay? If you cannot get them, that's useless, right? But just based on this definition, it doesn't tell you anything about how to compute it. You need to try all possible unit vectors along all directions and find the one that, after linear transformation with A, get the largest. Right? But it's not a computationally affordable. Right? You cannot try infinite number, even uncountable number vectors. Okay? So how do we actually compute these things? So this is actually what we care about. And this is what maybe you call libraries, the libraries do. Okay. So there's a method called the power method. So for SVD computation. Okay. So let's take a look at how we can compute this stuff. Okay. We know it exists, but how to actually compute it. Right? So let's first construct a matrix B. Okay. Remember, you have the A matrix, right? So we can compute A transpose times A. And this B matrix is a D by D matrix, right? Because A is n rows and D columns. Okay? And A transpose, of course, D rows and columns. It's just a reverse dimension. Right? And then you times this dimension matches, right? Then you can time, and the result is D by D. Okay? This is just simple matrix multiplication. But one thing that we can, what's interesting is that we can, even though the definition doesn't tell you how to compute it, right? But we have the conclusion. A is, you can write A as a shape, right? And A can be written like this. Okay? UI, the address. Right? You can write it as out, and you can also write it as out, and then okay? So what's nice about it is that this is basically what we just described. Right? So if you compute, let's go back. If you compute something, this thing transpose, right, will give you VI UI. This is actually go from this direction, 1B transpose. This is VI transpose transpose. Okay, I hope this is good. Okay with you guys. And then you compute this term times this term, right? So this is quite tricky, right? You think about this, R terms times R terms. So this is R square terms after product. Okay, every term here can times every term. But we can cancel out a lot of terms. Okay. Right. So why? You think about it. Hey, because ij we can have R squared so many terms. I can go from 1 to R. J can go from 1 to R. Right. And then we count these two terms. Right? And we take the constant at the beginning, and then this thing and this thing. Okay. Right. And you notice that this is UI, this transpose, this is UI. Okay? So this is here, it's in the product in the middle. So that's how we actually reduce the number of terms from R squared. Okay? Because you think about it, this is the inner product between UI and UJ, and they are orthonormal, which means only when they are the same, I equal to J, this is 1, this term is gone. Okay? If I and J are different, then this term is 0. So the whole term in the summation is gone. Right? You don't need to sum this term. Okay? Any questions? So how many terms actually remains? The answer is R terms instead of R squared. Right? So R equal to J is a requirement for this term to not be 0. Otherwise, this thing will be 0. Okay. So then you all have I equal to J equal to 1, I equal to J equal to 2, I equal to J equal to R. That's the number. So we remove a lot of terms. Okay. Now, if we have this term, right? So I equal to J, right? So from I to R, but J becomes I. Okay, J becomes R. So this thing becomes 1. Okay? So this is sigma I squared, okay, VI and the VI transpose. Right. Hope this is fine with you guys. So far what we do is go from the shape of A, which we know it can be SVD like this. We show that B can be represented like this. Okay. Any questions? So there's no V, no U, okay, only V term. But the nice thing about it is that now let's consider V squared. Okay. So the reason we want to eliminate U first is because we want to get this first compute V1. Okay. Now if we have V squared, so we can put this B here and we can put this B here. This is a transpose. Okay. And based on the same reasoning, just like here. Okay. So this is the VII transpose. VI transpose. Okay, so this term is symmetric, basically. If If you transpose this, it's still this. Okay? So this will gives you, it's basically, it's like it from here to here. So this term from here also to something like here. The difference is that now UI becomes VI. Okay? UI becomes VI. Right. That's the only difference. Right. And no matter how, this VI will cancel. Right. Right. So it will still be used. The only difference is now, each term is square. Okay? Each term previously is to the power 1, that becomes square. So if you have square times square, it becomes 4. Okay? So that's why we have the term 4. Any questions? All right, so we can continue actually. Right? So if you think about B cubic, B cubic is B square, this thing, okay? Right. So let me see how to say this. Oh, by the way, let me see. B square is actually B times itself, right? So why we have this transpose? The transpose, adding this transpose or not adding this transpose, it's the same. Okay. So the reason is very simple. You think about VI transpose. Okay. We take the transpose. Okay. So the result will be, go this direction. It's VI transpose. Right? The first one. Then take system transpose. VI transpose. So this again VI transpose. Right? So this term is a symmetric matrix. Okay, and adding a bunch of symmetrics is still symmetric. So whether we add this T or do not add this T, it's the same. That's why we add the T, because we want to have the same shape as here, so that we can show that the derivation is the same. We don't need to continue that way. Now if we have B cubic, it's equal to B square times B. Okay? And B square you can also write a transpose because it's a symmetric matrix. Okay? In general, if you have A transpose A or A transpose, it's always symmetric, right? Because you can take this transpose it. So from right to left, this A transpose. Okay? This A transpose transpose. It's the same thing. Now, if you do this, basically what we'll have is this B square will have a term sigma 4, okay? And the B will have a sigma 2, right? And this sum together to 6. Okay? So this direction is like this. But so in general, if you derive things like this, you have this. Right? So B to the power of K, sigma 2 to the power of sigma I to the power of 2K. Okay? So you can use the induction to show this, right? Because we show that 1 is 2. Okay? And to the power of 2 is 4. And to the power of 3, this is 6. Right? So this is really 2K. Okay? Any question on this slide? I hope this is fine. Now the last thing is that we have a bunch of VIs, right? So we don't have U, it's already cleaner. Let's assume, remember our singular values are like a sigma 1 larger than equal to sigma 2, like sigma 3. But sometimes it's possible that sigma 1 equal to sigma 2. Sigma 2 cannot go beyond sigma 1, but could be equal. Okay. We'll handle the equal case later. Let's now consider sigma 1 is strictly larger than sigma 2. So in that case, what will happen? Right, so here, if K goes to infinity, the first singular value, the first component will stand out. Basically, so here's how we compute this. Right? So just think about BK, right? Divide by this thing. Okay, divide by sigma 1, K, U1. Okay, so this will give you a summation, right? Each thing should be divided. Okay, right. So I think it's too thick. Let me adjust the thickness. Let me see how to adjust this. I think the canvas computing functionality is too thick. So let me try to pull out the pen. Otherwise, it's we cannot write too many. Let's pull out the pen. I think this is not so thick. So here's what we have, right? So BK divided by this thing. Okay, sigma 1, 2k, b1, b1 transpose. We want to show that as k goes to infinity, this thing goes to 1, which means the denominator and the numerator is almost the same as k goes to infinity. Right? So how to show this? Right, so you divide by the left hand side, you divide by the right hand side. Right, so this is divided by v1 transpose. Okay? And you also divide by this term. So this term you can take 2k out. This is sigma I divided by sigma. Okay? Now we know that any term starting from sigma 2 will lead to this term less than 1. Okay? And if you know that if q to the power k and q is less than 1, right, and then k to the infinity, this thing will go to 0. So the other terms will be gone. Right? Plus 0, 0, 0, 0. Okay? Only the first term, which is sigma 1 divided by this. This term will stand up. Okay? So basically this will be 1, this is our constant. So that's the first term. Okay? So we can see that really it's the case, right? If k goes to infinity, really the first term stand up. Okay? So in general, giving intuition, right? Don't need to go to the infinity. Right? So give some intuition why this thing can work. Okay, so I think we need to go to the previous slide to consider. It's very simple because as long as you have one term that is larger, that dominates. Okay, as you take the power, this thing gets much larger than the other thing at the power. Right? So finally, this thing dominates. Maybe 99.999% are from this company, the first company. So this is intuition here. So what's so nice about it? This means we can compute B, right? So previously we know we have the B, okay, which is some a matrix A transpose times A, okay, which is B. We can compute this B, and then we time this B with itself many times, okay. K go to infinity, really time the B a lot of times, okay. And finally, after maybe 1,000 times, you get this B, right? It's gonna be very close to this value, this thing, right? Okay, so then you know that if you do this SVD, right, so you just normalize the first column, it will be V1. Okay, the first column of BK will be V1, right? So how to see this, right? So you just think about sigma 1, 2k is a constant, right? So then you have V1 times V1 transpose. Right? V1 is a column vector of V1. Okay. Maybe x1, x2, okay. And this is this is a row vector now. Okay. x1, right? So if you time this out, if this is called auto product, and so if you are familiar with that, the first row times the first column will be x1 times x1, x1 squared. The second row times the first one, x1 is 2. And if you look at this element here, this first row times the second column, x1 is 2. Okay? So basically, it will give you something like the out product. Okay, so it will give you xb squared. Okay, it will give you basically the how to say this. This result, the ith column, and if you have this will give you a matrix basically. This column. If you look at the ith row and the jth column, okay, this term would be xi, xj, okay, something like this. Well, we are saying that if your v1 can be written as vector x1, x2, xp. Okay. If that's the case, then this term is, any two of them, I and the j's. Okay. Now let's look at what's the first column. Okay. What's on the first column? The first column is, the first row, x1 times x1. This is x1 squared. Then the second row, x2 times x1. Okay. x3 times x1. Okay. Blah 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 to x. How many of them? D. Okay. So that's the content of the first column, right? In the output. Now we just need to normalize the first column. Okay. Because when we normalize, basically we scale them. Right? So basically all this constant. So we just divide by x1. Then we get this stuff. Okay. Why normalize? Because this V is a unit vector. Right? So this less is 1. Right? So this column is 1. So put simply, after you get this matrix times this, so let me recap. Okay. So all you need to do is you get A times A transpose, right, which is B. When you get A, you can just do this, and you time it many times. You square this cubic, K times. Okay. And then finally, you get this huge matrix. Right? So then you take the first column and normalize it. Then you get the first singular value. Okay. So that's the solution. Right. So if you want to get the second, the third, you will be using. Let me see. We will be using that conclusion. I think somewhere. You just reduce. If you get a sigma 1 V1, then you can compute A1. Okay, and once you compute A1, you reduce it. Then you compute the next sigma 2, right, and V2. Okay, you just reduce the first one. Okay, and then you can recursively do this, and you get all the V. Because once the dominating component is gone, then the second one was done. So basically it's here. So then sigma 2 V2 transpose is done. Okay. All right, so but this method has a weakness, right? So this has a significant weakness because we know that the let's take it. Firstly, the drawback of this method is that D can be large. Right? You can have very high dimensional data, and the B matrix is D by D. Okay, it's a huge matrix, D by D matrix. Okay, and let's say 1,000 by 1,000 dimensions, and then you need to times this matrix with another matrix and get a times this and get another B square and then times another matrix, B cubic. You repeat the matrix multiplication, which is super expensive. Okay, and it's D cubic each operation. Okay? So it's like if you think about how to write your program, so you have two matrices which are D by D. It's the first row times the first column, second row times the first column, etc. So you have four loops for 3 times. Right? One time is for I and j, and within this item, the result, okay, you need to do another for loop, like inner product for I and j. So it's really cubic. It's 3 for loops. Right? So this is very expensive. It's a cubic to the number of dimensions in the data. Another thing is that maybe we can use some sparse matrix multiplication. Right? So for example, if your data is very sparse, right? Even though you have 1,000 dimensions, but most of them are 0, like in our documents. Right? Only a few words are included. That's fine, but once you compute B, which is A transpose times A, even if A is sparse, there's no guarantee after compute this, B will be sparse. B can become dense, okay? But because, when you do this, A transpose A, basically, A is first row, right? So this is AI transpose, A is second row, right? So, so basically, the results, there's no guarantee it will still be sparse. Okay? So then you are doing dense matrix multiplication for K times, which is super expensive. And we will improve upon this power method. Okay? And that will be a randomized algorithm. We will show you after the break. Okay? So we will take a 10-minute break. We will come back at 6. We will come back at 6:17. Okay, and be sure to be back on time. Yeah, I will be here answer your questions if you have any. Let me know. Any questions regarding what we discussed today? By the way, so we will not test the so difficult proof stuff, but at least you need to know simple conclusions. Okay, like A can be at least after going through so many things, it can be decomposed like this. You can write it out and then you can do some inference. So we will have a written assignment on this. Right. So be sure you understand these and understand something like these conclusions. Right? You need to know this and you can use them to do some calculation. Okay. that's needed. We will not test you very difficult proofs like in the slide. Any questions?
None so far.
Okay, so you can follow, right? Just want to make sure everyone is following. Right, so if you have no questions, I will come back. I think now maybe a little bit more than 5 minutes. I will see you in maybe 7 minutes. Okay, let's continue. So yeah, so maybe this stuff is quite difficult, right? So, but this is because our textbook, right? Previously, the textbook we strictly follow the textbook. Okay, so they are written by, you know, theoretical computer science people. Okay, so make the a lot of inequalities and the proofs and math, and so it will be a little bit difficult. Okay, but we only pick the most useful 2 chapters right now. Okay, we skip a lot of things that are too theoretical. Okay, SVD and streaming algorithms are quite useful. So this stuff, I think it's important. Right? And the student asked about how to, how to prepare for this content. I know it's very difficult, right? So the textbook, there's a SVD chapter. There's also a streaming algorithm chapter. Okay, we basically follow these. But I think the best way is due to follow our video and our slide. Okay, and if you cannot understand that the first time, you can rewatch the video. Okay, so that will definitely help. Okay, because these things are like again not simple. Right? So maybe this formula is using some conclusion from a prior formula. Right? But I would recommend you to firstly get an impression of what SVD is looking like. Right? So let me see this page. Okay. So you need to have so you have an impression of the SVD shape, right? And how it can be like these things are equivalent. Right? And then we have something like these. Okay. Once you have these things in mind, but these things are strictly derived. Okay. Right. But as long as you have this big picture in mind, it will be a lot easier for you to understand. Right, so previously what we covered is this, right? So we say that we can do a B matrix, which is A transpose times A. And we can, okay, we can times this thing K times, right? K to be very big times. And after that, we take the first column, okay? We take the first column, and that will be our result. By the way, for those kind of matrix linear algebra, matrix computations, you also need to know some conclusion. Is a so-called outer product. What is the outer product? You're familiar with that. Okay, we will see this again. Okay, and like a diagonal matrix, if you time on the right-hand side, it's like a scaling of columns. Left-hand side is scaling of rows. Okay, those things, if you need to react and for a long period of time, then it's very difficult to be efficient in understanding this stuff. Okay, some like formulas or like conclusions you need to memorize, just like when you compute derivatives. And the best way, again, when we encounter them, you try to memorize them. But if we can encounter 5 times, maybe you will memorize. Next time it will be easier for you. And yeah, so this method called the power method, it's very efficient because we time the matrix with the matrix again. So there's another solution called a faster power method. Okay, so you add a faster. So what is this method talking about? Let's take a look. So the faster power method is staying here. Instead of directly working on B, we will pick a random vector X, okay, d-dimensional vector. And instead of computing BK, we compute BK times X. Right. So why this is interesting, right? Why this will, firstly, we said that previously it's too expensive, right? Why this will reduce the computational cost? The answer is very simple. Right? So if you have an X, the first time you compute a Bx, Bx becomes, square matrix times the vector is a vector. So this becomes vector. Then you can time with another Bx again, right? And you do this operation again, okay? And then you time this again. Again, you get a vector. Right? So the next thing is previously we are doing matrix times matrix, which is d squared, okay? That's too expensive. D cubic. Okay? Now what you are doing is d squared. The operation is very affordable. Okay? So you have a factor of d, computation cost reduced, right? Previously you are doing matrix computation, multiplication. Now you are doing a matrix and a column vector multiplication. Right? The space is also very, very small. Here it's two big matrices. Right? So here it's two columns. Right. So this is why, when you time some random x, the computational cost will be different. Right? But after we get the random x, how can it be useful? How can it help us compute the v? Right? So that's the question. Okay? So again, here we are computing from right to left. Okay. So each time we have a column, times the matrix, become a column again, and times this matrix, and then become column again, times this matrix. So here, let's write x out. Right? So because we know that x is in our d-dimensional space, we can write using the radius v1, v2, all the way to vd. So coordinates are c, and c is coordinate, starting with c coordinate. And yeah, so if we write x out like this, okay, x is a d-dimensional space. So here, maybe we say, hey, this can be r-dimensional, but d is at least r. Right? So we just write out d. If some of them should be 0, beyond r plus 1, etc. C r plus 1 will be 0. That's fine. We just write it as d, okay, d-dimensional. Then what will happen is that now let's consider what we computed here. Right? What will it be? Right? So firstly, we know that bk, after k iterations, it will be almost equal to the major component, right? And x, we time x is this thing, right? We write it out. It's this thing, right? So what do we have? So we can show that, if you time this with this, this again, this is one term, this is a summation of term, but in the summation, this constant can go to the front. Okay, then we are timing these two terms. Okay? And anything I is not equal to 1. Okay, and the inner product between them is 0. Okay, so the only term that makes sense in the summation is c1 v1. Okay, c1 v1 times. And when it's c1 v1, then if you look at this term and this term, right, this cancels, becomes 1 because it's a unit. That's why you have sigma 2 squared, c1, right, and times this v1. Okay. So here is what we get. So if you compute this, but with the help of a random vector x, what you will get is this thing. Okay. Again, it's almost equal. Right. So why is it nice? This is telling you that when you time this thing is a vector value. Okay. Always the matrix times vector. This vector, when you times b on the left again with this vector, the ultimate vector will be a scaled version of v1. Okay, so that's very nice, right? So basically, you can scale it back, make it a unit vector, which will be v1, right? So this is our conclusion here. But this is only holding, right? So if only holding if sigma 1 is larger than sigma 2, right? Because then this 1k go to very big values, it will almost be the first component will be dominant. Okay. But what if sigma 2 can be almost equal to sigma 1, right? So in that case, then your first term may not be dominated. Okay. So even sigma 3 can be equal, right? You have the first 3 single values are almost equal, right? So then do we still have some guarantee that this method will work? Right. So here we have a theorem. Again, let's assume that x is randomly sampled x is a d-dimensional vector. Right. And we have to have an assumption. And we'll show that when you randomly sample x, this assumption will be easily met. Okay. If it doesn't match for one time, you try a few times, right? It will always, at least one time, it will be met. Okay. That's called a randomized algorithm. You introduce something random, but probability, this will always work. Okay. So failing probability is probably very, 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 very low. Right? And so here, let's think about what we are discussing here, assuming this conclusion is right. Okay. Assuming this conclusion. Right. So basically, your x has some small component along the first dimension. Okay. If that is the case, what will happen? So firstly, we want to consider this case. So which means your sigma 1 is very close to sigma 2, right? Sigma 2 is almost sigma 1. Sigma 3 is almost sigma 1. Sigma 4 is almost sigma 1. Okay? Maybe starting from sigma 5, it's a little bit far from sigma 1. Okay? So the others are all within a small epsilon to sigma 1. Okay? But the sigma 5 is significantly different, larger than epsilon. So this is what we are talking about. So you have J items that are not too far away from sigma 1. Only deduct a small portion, okay, sigma. So that basically accounts for that, like the first J components are all very large, okay. And even if this is the case, right, so what we can do is we, so let me see how this. So what we do is, remember this is a vector. We can write it as a W after we take the union vector. Okay, we normalize. And this W, let me see how to say this. If we do so many iterations, right, so this K is this K, okay? We time B on the right-hand side, right multiply the vector, okay, for B, K times, so many times, okay? Then what we will have is W has a component, okay, at most epsilon or something. What does that mean? That means if let's say here we are saying we have J sigma, which are all very close to sigma. Okay. Let's assume we have 3 dimensions: sigma 1, okay, sigma 2, sigma 3. Actually, it should be V1, V2, V3. Okay. We are just doing sigma 2. Okay. They are all very, your data have like a projection on these 3 dimensions are all very big. Okay. They're almost the same lot. So then we cannot discriminate each of the dimensions, but they are almost equal. Okay? So what we can do is we say, hey, now your V1, V2, V3, these 3 dimensions, constructing a subspace, okay? And you always have 1/3 of the content along each dimension. So basically, you are sharing this subspace. Okay. Where's my pen? So if that is the case, right? So this V is a subspace. Okay? V is a subspace band binding. Okay. Then our conclusion is this, right? So if you finally come to this W, right? W originally want to be close to V1, right? But we say that V1, V2, V3 are almost equally important, right? Any of them is fine. Actually, if your V is within this subspace, then you win. Okay? So we are saying that W is really in V almost, right? So at most, a very small epsilon amount of information outside V. Okay, W is almost all in V. Yeah. It's a linear combination of V1, V2, V3. Remember, W is a unit vector. So if you have, the length is 1, but you have a very small epsilon component outside, then most of the components are in this. That means that major, V1, V2, V3, if that equivalent in the combined space. So in that sense, this V is equally good because now this space is so important. Any vector, you can refine the 3 new bases. That's fine, as long as it's in the same space. Any questions? So this is what the theorem is talking about. Right? So this is just the theorem repeated so that we can do some derivation at the bottom. Okay. Now let's look at this iteration number. Is this reasonable? Right. So what does this tell us? So this tells us that if you want to be very strict, right? If I only allow 10% of information outside my V, okay, then 1 by epsilon is 10. This is 0.1, 1 by 0. If I only allow 1%, right, then you need 100 iterations. If you look at this, right? So this is reasonable, right? How much you want to be accurate, how much you pay. Right? But 100 iterations is okay because computing, right? Another thing is this, right? So this trend is the same, okay? This trend is the same. And the delta is also the same. But basically, if your sample, right, as long as you have significant delta outside, right, then it will reduce this number. Okay. What's more interesting is you take the log, right? This is log with base e, right? So usually here, what's in here will be a big integer or a big number, a larger number. So the reason is very simple. Think about it. If you only allow, let's say, sigma is 0.01, right, 1%. Delta, we know, with sample, we want to have some component, but this component in the worst case can be very small. Again, 0.0. Okay. Then if you time them together and 1 divided by them, it will be what? It will be 10 to the power 4. It's pretty large. Okay. But that's fine. So because this term has a law in here, right? This is law. Okay. So this will bring this number to a very small number. Okay. If you cannot see why, you just think about base 2. Right? So the law is e, right? 2 and e are not so far away. E is 2.8 around. Okay. So this log 2 to the power of a number. Right? So now let's consider a number that is really big. Right? We consider a billion. Right? So we can write this a billion into 1,000 times 1,000 times 1,000. Okay. 1,000 is very close to 1,024, which is 2 to the power 10. Okay. So this is also 2 to the power 10. It's also 2 to the power 10. Okay. Then 2 to the power 10 times 2 to the power 10 times 2 to the power 10. This is very close to 2 to the power 30. Now log base 2 and this 2, this gives us 30. Right? So even if what's here is 1 billion, right? After taking log, it's 30. Okay. So that also shows that this iteration is very reasonable. Okay, because you only need 30 times what you originally have, maybe 100. Now 3,000 iterations, you're fine. Okay, you max this requirement. Any questions? Okay, so if not question, let's continue. Next, we will prove this. So it's not so simple to prove. Let's see why this is the case. So the first step again is to do our SVD. A can be written in this shape. Again, now you should be able to know that A is written in this shape. Okay. If you don't know how to memorize this, just keep in mind we have A equal to U B transpose. Right? So V transpose, if you go to the element Y, this is small v transpose. U before V. Right? This D, when you write it out, it's going to be. Okay. So the shape almost you can memorize this in some way. You cannot see immediately. And how we can show that UDV transpose is equal to this? We have shown that before. So you can refer to the last time's video. Okay. Probably the one before. Because we have covered this topic for 2 lectures. All right, so how to prove this, right? So what we will do is we'll augment. Although we know that, hey, we only need R dimensions, right? So the A only contains R dimensional space, but A is actually in D-dimensional space, right? So because we have so many points, okay? It's just that this D-dimensional space can fit into R dimension, just like if you look at all the vectors in this screen, okay? Right? So they are in they can fit in the 2 dimension, right, which is the screen, but they are in the 3-dimensional space, okay? Each vector is in our 3-dimensional space. It's the same. Now, even though you only have R-dimensional information, we can expand additional field, right, in the null space, okay, of A for them. Right? So we can expand them into D-dimensional space. But the difference is that there are components. There's no components starting from R plus 1 to D. Okay? So this is possible. So we just expand it anyway. Right? So the reason we want to do this is because later when we do derivation, we need it. So now let's consider X. Right? So because X is, in D-dimensional space. That's why we need to expand to D, so they're in the same dimensional space. So X can be written like this, because X has no guarantee you are belong to only R dimension. It's you randomly sample X in a D-dimensional space. It doesn't have to have no component outside the R dimension. Okay? And if we do something like this, what will happen? Again, why we sample in D-dimensional space? Right? Why we can just sample in R dimension? This is also because when you do SVD, okay, when you do that, you know N and D, you never know R. Right? You only know R when you do the SVD and you finish SVD. Okay, so when you initially, in order to do SVD, you will sample from D dimensions. You only know D. Only if you finish SVD, you know what's R. It's if you think about V1, V2, how we get it. Okay. And so when we write X into this D-dimensional space like this, right? And then the first iterative vector, this thing is equal to this thing. Okay. How to see this? So this BK is from our previous conclusion. Let me see. From here. Okay. Basically, you remember we do this derivation here. No. Okay. So BK is this, and X is this, which is in this, right? So now let's see how to expand these two terms, right? So what we can do is, again, it's the same. So this constant can move forward. So you think about any term here, you have a summation of so many terms to match this term, and only one term will do the inner product, which is I. The other term will be 0. Okay? So basically, this I with this term will become 1. Okay, this will cancel. Okay? So basically, it finally gives you, of course, this constant should move forward. Okay, like this constant move forward, and then these two items. Okay? So this will be the result of this seemingly complicated stuff. Okay? Now we are using our conclusion that along the first dimension, the coordinate is at least sigma or delta. So here, and if that is the case, we can show that the component, this is a vector, the vector length square is equal to this one. Okay? How to see that? This is just using our concluding using this. So because BK, this vector is something like this, which we have d-dimensional, these are the coordinate bases, okay? And each coordinate V1 is this one, and V2 is this 2. So these coordinates, then if you want to compute the vector length square, it's really each coordinate square, okay? Sum of that, which gives you this. This thing square is this 4K and the 2. Originally it's 2K anyway. Okay. Is this okay? Yeah, let me know if you have questions. Okay. We can stop and go through this. And now we are using this conclusion. Right? So a summation of so many terms. Right? So of course it's larger than just the first item. Right? It's 1, 4K, 3. Okay. And this is very loose, but this is sufficient for our derivation. And because we know that along the first dimension there's some small component there. Right? So it's actually here, so this thing is at least delta. That's why we have this. Okay? So our conclusion is that the vector length is at least so many. Okay, so this is the first conclusion we have, which is copied here again. Okay. So this is the total vector length, right? And next we want to show that within this subspace, right? What's the vector length? How much information projection to the subspace? Okay. So here next, let's look at the squared component orthogonally, right? So which means instead of looking at how much is of this vector, right? The total length is this. Okay, how much inside is V, right? Now we will look at how many information outside orthogonally outside. Okay. In order to do that, we are doing something like this, right? So basically, so this is the V1, V2, V3, or VR. Right? Now this is inside this space. Okay, so let me see how to. so we assume M. Okay, so M is actually J. Okay, this J. We are saying the first. So this J. I think this notation is a bit confused. So sigma 1, sigma 2, sigma M are equally important. Okay, almost equally. So that's the M. So we are saying that hey, V1, V2, all the way to Vn, the first m-dimensional are like V1 is for sigma 1, Vm is for sigma 1. They are equally. Okay? And then in that case, starting from m plus 1's dimension, so Vm plus 1 all the way to D are outside your space D, outside the space. Right? And we want to compute how many components are outside the space. And you look at the vector length computation, right? It's actually a summation over the terms, right? The first m terms are the vector length squared inside the V, okay? And the other component outside V is captured by this. Right? It's like a Vm plus 1, Vm plus 2, V all the way to Vt in that orthogonal remaining space. How many components? What's the vector length of the product? Okay, vector length squared. So this will be this amount, and we can show that So this is using this this is using this computer. Right? So we know that for first m of them, it's a larger than equal to this. That means starting from m plus 1, right? Starting from m plus 1. And beyond, okay, m plus 2 is we have this 1 minus x. Okay. So now these i's are all like this, all like this. So now it's so that's why it's less than equal to because it's short. Right? And sigma 1 instead of using sigma m plus 1 or m plus 2, you become sigma 1. This thing we replace with this thing to the power 2. Okay. That's why we have it. Okay. And by how to say this? So array in this n plus 1 to D, array term is less than equal to this. So if we put this, then this becomes upper bound constant, and we can take this out, and then the summation becomes this. Okay. So now we want to get rid of this term. Right? So we know that C1, C2, C3, etc. are unit vector x. Okay, this x vector's coordinates. Right? And we know this is x is a unit vector. So their coordinates sum the square equal to 1. And if you miss some items, the first n item, this thing is less than equal. Okay? That's why we have this term is less than equal to this. Okay. So now we are quite close to our conclusion. Remember, we are doing W, right? W, we need to normalize it, right? So you do the B, K, X. Basically, X times B, left multiply B, and then multiply B again, and do this K times, okay? And then we say that, hey, this vector, we want it, and the vector, we want to normalize it. Divide by the length of this, this resulting vector, okay? And we want to show that this vector is in this V space, mostly. Okay? Outside the space, only as epsilon component. So the component that is orthogonal to the V space has square length very small. Right? If you remember, so this square length very small is here, right? And we know that in the denominator, right? It's the same shape, it's the same direction. Okay. Right. And in the meanwhile, this is a denominator. Right? This is a component like epsilon. Okay, like what's outside. And the total is here. Okay, but the total is in the numerator. So the numerator is divided by, right? If you divide by something, so the shape is reversed, which is again consistent. Okay, but the sign direction is reversed. So simply, it's like here you make this larger. Of course, it's upper bound. Okay, now you make this smaller. Okay, but you are dividing by some smaller value. You make it even larger. Okay? So we can get this conclusion that square length is less than equal to. Okay. So let me see. So squared length, right? So here is a squared length. So what if you just look at the again, so if you look at here, right, this sigma 1 and sigma 1 will be canceled. Okay. If they cancel, actually, it looks like magic, but you can see we always try to take out sigma 1 in some way. Okay. The previous one, we also took out sigma 1. Okay. One is using this conclusion, and the other is dropping the other summations. If you look at the previous one. Okay. Dropping the others, only keep this sigma 1, but the other term. So we are purposefully try to get both, denominator and the numerator have only sigma 1, so we can cancel. And then after canceling, it becomes only 2 terms. Right? So one term is this, one term is this. Okay? And then this is square length. So if you just take a square root, you'll get this. Okay? Any questions so far? I hope this is fine. Okay. So next, next we are using an interesting conclusion. This conclusion is telling you, this is another inequality you need to know. Okay? 1 plus x is always going to be less than or equal to e to the power. Okay? So this conclusion you need to memorize. And this holds for any x. Okay? So how to make sense of it? Right. So firstly, what is again? So this is to stick. Okay. So let me use something thing. Okay. So we are getting this conclusion. 1 plus x is always going to be less than or equal to x. And this holds for any x, right? Which means if you take a minus x, it still holds. 1 minus x is less than or equal to e to the power. How to see this holds for the whole domain from negative infinity to positive infinity? Right? So you just think about the shape. Okay, so this is x, this is y. Right? So if you look at the first function, right? So let me, so the first is y equal to 1 plus x. Okay? So y equal to x is this line, right, in the middle. 1 plus x, if you look at x equal to 0, y equal to 1. So this means you need to move up. Right? So this is 1, this is minus 1. Okay? So this will be 1 plus x. Okay. Next, let's look at this. Right? So which means we want to look at another function, which is y equal to ex. Right? So what will be the shape of that? Y to the ex will be exactly something like this. Okay, and it goes infinitely to close to 0. Okay, so it's always above. It's always above this 1 plus x. Okay, that's why this can be true. How to see that? So we know that ex is some shape like this, right? And here it's exactly 1, because when x equal to 0, e to the power 0, y equal to 1. Another interesting thing to see is that the slope is faster, which means the distance will be larger. Okay, and actually they cut cross right here. Okay, it's a tangent here. Okay, y. You think about this. This y equal to x. Right, this is 45 degrees. You look at this is 45 degrees. Okay? But interestingly, if you look at the slope here for this function, okay, for this function, it's also 45 degrees. Okay. Again, if you want to prove that, it's another way is just to move to the right hand side and take the root. So then you will see that. Okay, it's very simple. But you will see, hey, this always holds that slide. But here we are helping you to pictorially immediately see this completely correct. Okay. So this is because if you look at the e to the power x, if you take a derivative, it's still e to the power x. Okay. And if you look at the derivative application x equal to 0, so which means k x equal to 0, then the derivative is 1, okay, e to the power 0. And so you know, this slope is 1, and this slope of 45 degrees also 1. So which means they are kind of parallel. So then you know, this can only become faster if they pull away, and this will you know, also above it, because this becomes you know, less than 1. Okay, and this is continuous 1 to go down. Okay. So you can either see that this completely holds all the way from negative infinity to positive infinity. But so besides the previous Bernoulli inequality, this inequality is also very important. Okay. I hope you are okay with this. So if you know this, then things get super simple. Okay. So what is E minus 1 minus E? Right? So 1 minus epsilon. Right? So we told you it's gonna be less than or equal to E to the power minus. Right? Previously we tell you X, right? Epsilon, just replace X into epsilon. You will see. Okay. So then you can see that basically we are saying, let me change to the right. So if this thing to the power 2k, and this is 2k, which is divided this thing, divided by that. So we get this thing. And finally, if you put the k here, so this k is equal to this value, this k is equal to this value. And if you put it in there, you know, so this 2 epsilon cancels with this 2 epsilon. Okay? And this will give you line and 1 divided by epsilon. Okay? And you know, line, if yeah, let's do this. Okay, so if you put this thing here, it will be equal to E to the power of line. Okay, and this. Okay. Again, there's a negation. Negation of line epsilon there to the power minus 1. Okay, and you know that line something to the power minus 1, you can move it forward. And the E and the line can cancel. Okay? Yeah, because it's racing. Okay, finally you get the denominator becomes epsilon delta, and the delta cancels, which becomes finally epsilon. That's why you get this. And you may feel a little bit confused why you know, people pick k like this. Right? So the answer is very simple. They solve this equation and they see what is k. Okay, so that's how they get this k. But then this k actually makes sense. It's not too many. Okay, we just explain why this is acceptable. So if you put this thing exactly equal to epsilon and you solve for k, you look at this. Okay. Any questions? Okay, if not, then if you make it epsilon really strict, 99.9% are actually, you know, inside of E, which means our vector is very accurate. Okay, almost in this subspace, which all the components are very important. But the question here is we have an assumption, right? We assume that if we randomly sample X in the two-dimensional vector, right, we have some guarantee that, you know, it has a component coordinate along the first dimension, V1, okay, for the A matrix. It's gonna have some component, no less than that, okay? But how can we guarantee this, right? We have no way to guarantee this for 100% times, okay? But we can make sure the probability of failure is very low. This is called WHP, with high probability, okay? So this is what we call the randomized algorithm. So let's first look at the conclusion, and we will take attendance, okay? And then we will continue deriving the rest. So how to sample X, right? So firstly, how to sample a unit vector X in the r-dimensional space, right? Another question is how to set k accordingly. So especially you have this their values. So the choice of x, let me see here. The choice of x is this, right? So, you know, we want x to be a unit vector. So this is a really difficult example. How can you guarantee you will immediately get a unit vector? But instead of getting a unit vector, we actually can sample from a unit ball. Okay, so there's a actually it's not so simple. There's a paragraph in the textbook tell you how to sample from the unit ball, which means in the d-dimensional space you can sample point within a hyperbole, right, of radius less than or equal to 1. It's like you are sampling a point with x1 square, x2 square, call it x3 square, less than or equal to 1. Okay? Now how to sample from this hyperbole? Okay. And so there's a way to sample this, right? And after sample this, your vector length, right, is going to be less than or equal to 1. Okay? It's not going to be equal to 1. Then you can normalize it. Again, so as I said, so the how to sample from a board itself, there's a chapter in the textbook. It's not so trivial, okay, but it's a well-known method, so you can look it up. Okay. And then once we have that method, we can normalize it, and then we get x. So that's also the reason why we finally derive value using unit ball, because you can randomly sample a point in the unit ball. Okay. It's actually a very theoretical chapter. We skipped it. It's probably the first chapter in the textbook. So now let's see if we can do this in a unit ball. We can sample x and then normalize it to make it a unit vector. Right? Then we can show that the probability that the first coordinate, right, this first component, has at least delta equal to this amount. The probability is going to be 90%. Okay. Right. So here in the previous method, we can set delta in the past problem. Okay. So what does this mean? This means that we need to show this, okay, in the next few slides. But if this happens, so which means this assumption holds, right? So this assumption here holds with 90% probability. Okay? You succeed with 90% probability. Okay? So what's the probability of fail? Who can answer me? What's the probability of fail? Which means you don't have a component larger than or equal to this value. By the way, D is a dimension, okay, so you can square root dimension, but this is still reasonably large. Of course, you have more dimensions. You should try. This problem will be more difficult. You should, you should time do more power iterations. Okay. So that's reason. So who can tell me? So if you succeed with 90% probability, how likely you will fail? Which means the previous property may not hold, and so this may not hold. Who can tell me the probability of failure? I hope you are still following. Okay. Yeah, if we randomly pick like this, okay, the failure probability is 10% or less. Okay, failure succeed probability 90% or more. Right? Okay. So randomized algorithm always do something like this. We repeat many times. Okay, if you one time you fail, you repeat 2 times, 3 times. Okay, if your failure probability will be significantly lower. Okay, decrease exponentially. And that's why you finally, you have some guarantee. Right? This is also if we factorize a larger large numbers into 2, right? So finding larger primes. Okay, we are doing something similar. Okay, so here the failure probability is less than or equal to 0.1, 10%. Okay, so the first time you fail is this. The second time you fail is also this. Right? They're independent times. The third time you fail is this. Right? After 3 times, you're already to 10 to the power -3. Okay. If let's say we will try this 100 times, okay, so probability of fail is 10 to the power of 100. It's almost negligible, okay. But so if you repeat this a couple of times, the probability is already reasonably small, okay. That you still cannot find a V1 that is meaningful. That is good. Okay. So as long as you can show that each time your probability of failure is a small constant, you can repeat, and enough times, and then you can bring it down. Any questions so far? Okay, if not, next we will take attendance and then we will prove this theory. Okay. We can even need a window. And let's go to canvas. I think it should be I think the PhD list, the student already asked my question.
Professor, I'm here.
Yeah, so I know, so I just let it. Let's sample randomly, okay? That's from the third one, and the average 3 will pick. Okay. Hada, are you here?
Yes, I'm here.
Okay. Muhammad, are you here?
I am here. I'm here.
Okay. Gayatri, are you here? Gayatri? No?
Yes, sir, I'm here.
Okay. Yeah, Mahesh, are you here? Mahesh Bang? No? Chen Yuchen, are you here? Chen Yuchen? No? Mohammed?
Yes, I'm here.
Tom?
I'm here.
Okay. Alakia, are you here? Alakia? Alakia, are you here? No? He?
Yes, I'm here.
Philip?
I'm here.
Me? Ming Li? Me? No? Abhilash? Abhilash, are you here? No? Oh, that's a lot. Okay. Pranav?
I'm here. I'm over here.
Okay. Saga? Saga?
Oh, yes, sir. I'm here.
Okay. Santosh?
Yeah, I'm here.
Got it. Sandy?
Yes, I'm here.
Saili?
Yes, I'm here.
Madhu?
I'm here, sir.
Got it. Katha?
Yes, sir. I'm here.
Connor Susis? No? Sushmitha? No? Oh, I see chat. Okay, I will fix that later. I will come back and fix. Amelia. Amelia?
I'm here.
Hamid. Hamid, are you here?
Yes, sir, I am here.
Frank? Frank who?
I'm here.
Ryan? Ryan?
Yes, I'm here.
I will fix chat. I think there are like 4 chat, maybe Alakia. Okay. And you're welcome. And anyone else that I somehow missed? Not, then let's continue. Okay, so let me see. So the attendance is not so good. 3 students, probably 4, 5, 6. Yeah. All right. Thank you. Okay, so so for the faster power method, right? So we require there's a small delta component, okay, along V1. Okay, and is it again? So it's reasonable if you know, because this delta influences the K. If you remember, right? Delta small, then your K should be more. But that's reasonable because please. Okay. Just a moment. I think a student tell me this again. So yeah. So further attendance issues, just send me email, okay? Because you cannot. It's occupying everyone's time. Well, I call your name. Hopefully, you can respond in like 2 seconds or 3 seconds. Otherwise, it will take too much time. Okay, let's continue. And when this is smaller, right? So which means 1 divided by delta will be larger. Okay, K will be more. Okay, but that's reasonable because if your dimension is higher, right? So this value will be smaller. You need to run more iterations. But D is higher means the problem is more difficult. Okay, so that's reasonable to get this value. Okay. So next, let's look at why this probability is 90% or larger. How to prove this? So firstly, let's look at, we are sampling from a unit ball of D-dimensional space. So we are sampling X from here. And let's look at the probability that, and here's this unit ball is something like this. Okay, so this dimension, you see we only show 1 dimension. This dimension is your V1, okay? It's your first dimension. All the other dimensions are kind of hidden in this dimension. This is V2, V3, all the way to 5. This is actually a D-1 dimension kind of hyperspace, okay? Because it's not easy to show that. So we kind of showing like 3D space, but actually it's a hyperspace, okay? So we isolate our 1 dimension, okay? Oh, actually, I think that this is V1. This is V1, so this is V1. And so this is V1, okay? And you look like this like a disk, but this is not a disk. This is actually a hyperbole of D-1 dimension. Okay? So this is how you read it. So now let's look at how, if we, we wanted the probability larger than this value, alpha, okay? So what's the probability that your let's say you have a hyperbole, like you pick this point, okay? And if you look at this vector, the component here is within alpha, okay? Within alpha. What's the probability? So the probability is something like, which means if this is V1, okay? So this is origin, okay? So it's like you are within here. So your point is within here. Then your component will be within alpha, which is not good because you want to be larger than alpha, okay? So let's look at what's the probability to be within this zone. Right? If you look at this ball, pocket ball, if you sample point within this zone, you're not sample outside this zone. Okay. So actually we can derive an upper bound. Right? So no, we can make it a little bit larger. Okay? We are doing something like this. Okay? So this is basically what we are doing. So we are using this disk. You can see this disk. This is the upper half. Okay? We have a bottom half also. So that's why, you know, if you look at the both space, this space is this. So we have the denominator is this, but this is the upper bound because this goes outside the ball a little bit. Okay, and the lower bound is the whole volume. This V means volume of the D-dimensional unit ball. Okay, this is a unit ball, which means it's a radius one. Okay, we are sampling from unit. Okay. So now we want to sample from these two disks, right? So that any point sample inside this ball, the component within R. Okay. And this is upper bounded by, if we go out a little bit, right? And how to compute this volume? So the volume is computed like this, right? So you look at this D minus one dimensional ball, right? So as we said, this disk here is D minus one dimensional ball, okay? So this is this, right? And the radius here is 1. Okay? This is actually a ball, a hyperbole of D minus one dimension. You cannot plot it, you know, otherwise you cannot visualize it. It's a high dimensional space. Right? You just think about this as D minus one dimensional ball. Okay? And this is again a unit ball, right? So the radius 1. So we can write the volume as V to the ball volume, but in the D minus one dimension. Okay? But here we will go to alpha up and alpha down. Okay? This gives you the space within this one. Okay? Any if you sample the ball, anyone within this range, the mapping to V1 will be within R. Okay? Of course, it's absolute value, right? Will be within R. Right. Let's take a look at how we, you know, if this is the case, right? So this is really the case, right? So this is really the case. Okay? And then if we set alpha equal to 20, right? So because, you know, we want a V1, the component to be larger than this, okay? But we want to go outside this two segments, okay? We want to go beyond this segment, here or here. But so when you are inside here, you fail, basically, okay? The component is less than what we require, like this, okay? So here, alpha basically is this value, okay? This value. Right. This is a failure probability. Is this okay? Well, this thing is a volume of a unit ball, right, of D dimension or D minus one dimension. This cannot give us a constant like here. So we need to further operate on this and finally reach something like this. Okay? Again, we are computing failure probability is 1 by 10. Okay? The success probability larger than 90%. Failure probability less than 10%. We are showing the failure probability. So next, how do we do this? Right, so we want to cancel this VD. Okay, right. So we want to turn the VD into a function, into some term that has VD minus 1 here. Then we can cancel the VD at the top and the bottom. Okay, which is here. Right. So basically, we want to show that. So let me give you the conclusion. Right, the conclusion is VD will be larger than or equal to VD minus 1 divided by square root D minus 1. Okay, and then if you put VD, put it here, and remember this is making things smaller. So this will divide by something smaller, it makes it larger. It's still okay. And then we can cancel this VD with this VD. So this is our motivation. Right? But how to prove this conclusion? Right? So of course we can memorize this conclusion. This always holds. Okay. So but how to see that? So this previously we are saying that we use a disk that goes out of the ball. Right? So here we will need to use another disk that goes inside the ball. Right? So because this VD is upper bound, right? We want to have something contained inside the ball. Right? Then this volume is on the right hand side. Okay. So how to do that? We are looking at a cylinder of height. So we are looking at a cylinder here, inside. So this cylinder has a height of this size, and there's a radius, right? So if you are still inside the ball, yeah, basically we are basically considering this piece of disk. Okay, so basically we are considering something inside. Okay, and we want to show that for this cylinder inside the ball, its volume is something like this. Okay, so this is what we are trying to do, and we know that the height of this is 1 divided by square root d minus 1. The reason we do this is what we derive this. Basically, you can have other things, but this thing can elegantly give you v d minus 1. That's what we're doing, right? And the radius, right? So now let's think about it. Okay, let's think about this is a unit ball. Okay, so this radius is 1. Okay, and we know this. If you look at it, you know, so how to say this? Let me change the color. So this is x1, right? Just because this is the first dimension. Okay, x1. This is v1. Okay. So we know that x1 square plus maybe x2 square, right? Plus x2 3 square. Okay. Let me try to use the pen. X3 square plus plus xp square, right? Is equal to 1, right? Because this thing is 1. Okay, I hope this is clear. Right. Now, what is x1? We told you x1 is this height. So x1 square becomes 1 divided by d minus 1. Okay, because it's square root. Right. And now, based on this, what is x2, x3, xd? Right. So we say x2 square plus all the way to xd square. Okay. This thing is equal to what? This is equal to 1 minus 1 divided by d minus 1. Okay. Just to move this thing to the right hand side. Okay. So what is this? This is basically this thing, right? So this is, remember, this is d minus 1 dimension from 2 to d. This basically how to say this? Yeah, if you think about this is the radius in this ball, okay, in this d minus 1 dimension. Okay, apparently this is the radius after removing the first dimension. Okay? So this is 1. Sorry, so maybe it's so basically this thing, right? So we get. So next, based on this conclusion, right, so we know that if you look at this piece of disk, okay, so radius is this, okay, right. And this is, remember, x2 square plus xd square, okay. So this is not radius, this is radius square, right? If you take a radius, okay, right, then that's the true radius. So you need to divide, to the power of 1 by 2, okay. Right, so far we know that we have a ball, 1 minus 1 dimensional ball. The radius is something like it's a radius of 1 by this, take square root. Okay, but this is the radius, right? But our ball is a d minus 1 dimension. Okay, so you need to the power of d minus 1. Okay, so this is like if you have a cubic, right? So 1 1. Right? So if you have 1 dimensional, another is 2, then 1 2 factor 2. Right? On the other hand, if it's 2 dimensional, right, it's 2 squared becomes 2. Okay? If it's 3 dimensional, then the cubic becomes 2 to the power of cubic. Okay, right? So it's the same. Okay? It's just to the power of how many dimensions, right? If you d minus 1 dimension. Right? You just think about the volume is finitely small, many cubics. Right? So then you can see. Right? So that's why. So this is the radius of this disk. Okay, and then because this is the radius, and we have so many dimensions. Okay? So you think about it. So 1 dimension is this. This is what? This is Vd. Right? Now you shrink the radius by this ratio. Okay, but you shrink this only along this radius dimension, but you have the space is d minus 1 dimension, so you need to time d minus 1. Okay, so that's how we get this thing. So this basically gives you the cylinder's volume here. Okay, But you have another dimension, which is this dimension. Right? So this dimension is, this thing, right? And this thing again. So it's twice. Right? So this gives you the whole volume inside this thing. And we know this, if you sample point in the cylinder, right, the volume is going to be smaller than the whole block. So that's basically what, I know it's a little bit complicated, right? So in the high dimension space. Right? This is because we skipped the first chapter, which is quite theoretical, but I hope you can see this. Right? And because of this reason, I hope we can finish this too. Okay. Because of this reason, now we are using something that we are quite familiar. If you remember, we want to cancel these. Right? So we want to put this here and then do the times. Okay. If we do this, if you remember, we have the generalized Bernoulli inequality larger than or equal to, because let's go back to there. Okay, so because this number is going to be larger than 1. Okay, either negative or larger than 1, it will be larger than 2. Unless you are between 0 and 1, you are small. Okay. But D is a very high dimension. Right? -1 by divided 2 is still a number larger than 1. Okay, and then you can say this larger than or equal to, you just times down. Okay, and this so that you can cancel. So after cancel, this term becomes 1 by 1 by 2. 1 minus 1 by 2. Okay, and this 2 cancels this 2. Right? And which left 2 with these 2 terms. Okay. So again, so it's super complicated. V is a volume of unit ball, which means radius 1 ball in the d-dimension space. Okay, equal to volume of a ball in d-1 dimension divided by, square root d-1. Okay, but this is upper bound. Okay, so this is tighter. This is smaller. Okay, on the right hand side. Hope this is okay. Again, it's not easy, right? So I hope you can see this. Right, so this is the final conclusion that we will be using, which we will copy here. Now we have 2 conclusions. One is this, which we use the cylinder going outside. Another is this, we use the cylinder going inside. Okay, then we can show the graph, because this denominator is still denominator, but this VD we can shrink it. This right hand side can only be larger. Okay, so we shrink it. We put this here instead of VD. Okay, and what we get is, so firstly, these 2 cancel. Yeah, these 2 cancel. That's why we are doing this. Another interesting thing is that we know that alpha is this one. Yeah, so we put in this one. So twice alpha is really 10 square root. Okay, so here we because this is as a numerator, so we put p. Okay, but the alpha is in denominator here, but in the denominator it's 10 square root b is on the numerator. So it's down. This is 1 divided by this, but it's in the numerator, so it flips up. Okay, so it becomes square root d minus. Okay. So finally, this is pretty simple. So this thing is smaller than square root d. You enlarge the square root d, then you can cancel 10%. Okay. So your failure probability, you happen to be in this disk. Okay. The failure probability with less than this is only 10%, which means your success probability is 90%. Okay. So if you fail the first time, but 10%, it's fine. You try another time, it's 1%. Okay. Third time is 0.1%. Okay. If you try 10 times, the failure probability is 10 to the power of -10. Almost you will always get U1. Okay. So that's the idea. Yeah, I think let's finish this. Let's see how many slides we have. Yeah, I think this is basically very end. Okay. So singular vectors, singular values, we have a recap, right? So the right singular vectors. So if you remember our conclusion, right? So right singular vectors are eigenvectors, A transpose. So this is what we showed in a previous slide, and sigma I square are eigenvalues of A transpose. This, remember, this is our B. Okay. Right. So if you remember B, we only have B, right? And the value becomes square. Okay. Because we have B and then we have B squared BK. Right? Left singular vectors are actually A transpose. Okay? And their eigenvalues are still this. Okay. Sigma I square. Finally, we have this complete. I think we can show this next time. Okay, it's a little bit long. Okay, so that's basically the end of this class. It's quite intensive. Let me know if you have any questions. Okay, I will be here for maybe 2 more minutes.
Thanks. See you next week.
See you next week.
Thank you. Bye.
Bye. Yeah, feel free to ask if you have questions. Thank you. Okay, I do not see any question coming in. So I will end this session, and then let me know if you have any question by sending me. I see another chat. Oh, there's a requirement to extend the deadline of the assignment for the midterms. So if you want to extend the assignment, send me email. Okay, let me know. We will see how many students you just extend. We can extend the assignment. We understand the midterm is, you have a lot of midterms, right? But if we do this, we need to do this for every student. Okay? If you really want to extend this deadline, just send an email. Okay? We will see. Okay? We can extend 1 week. But if it's only 2 or 3 students, then we probably will not do it. If there are a lot of students, and we will consider it for fairness, right? Because we will need to extend it for every student. If only 2 students cannot handle that, then, basically, if we extend, it's not fair to the other students. Our assignment deadline is always 2 weeks. A lot of courses, they only have 1 week deadline for themselves. Okay, so yeah, I will see you guys next week. Have a nice evening. Bye.